Right, so let me explain really quickly how the data bus and the registers work in the register transfer machine, which are part of a CPU. So what is a data bus? Well, a data bus is quite simply just some pieces of wire that all go in the same direction throughout the CPU, passing via various different places in the CPU. So in the case of my CPU, there are 8 pieces of wire, which is why it's an 8-bit CPU. And the way that this is done then is that a number is put onto the address bus to be transferred around by converting it into binary. So let's say we wanted to put on the number 170 onto the data bus. Well, 170 in binary is 10101010. So 170 in decimal is 101010 in binary. So we've got 8 bits labelled from D0 to D7 on the bus. So we would put 10101010 on the bus, and we would be transmitting the number 170 on the bus. So anything that's connected to the bus would be able to read that value 170 off the bus. So when we say we put a 0 or a 1 on there, well, a 0 is 0 volts and a 1 is 5 volts. So we put either 0 volts or 5 volts on a line of the bus in order to set it to either a 1 or a 0. So we can have on our 8-bit data bus various different things connected to the bus. So we can have an input device like one of my keyboards, the 8-bit switch keyboard that can produce an 8-bit number and put it in as an input. We can have a display, some sort of 7-segment display that could be sitting over there, that's an output. And we could have a bunch of registers which store an 8-bit number. So we could have registers sitting in here, and they're all connected to the bus. And the way that they're connected to the bus is simply by connecting 8 wires between the input and the bus, or the register and the bus. And everything that's connected to the bus is permanently connected to the bus, and is able to do one of two things: either to put a value onto the bus, which I call publish. I think some people call it asserting data onto the bus, but I like the word publish for that. And reading data off the bus, which in the case of a register is a store operation. So if we read some data off the bus, we store it in the register. One way or another, we're putting data onto the bus, or we're reading data from the bus. So we could, from the keyboard, put some data on the bus, and register 1 could read that data. It could store that data in register 1. Now, there is one rule of buses, and the bus rule is that only one thing connected to the bus can be publishing at any given time. So it's a little bit like when you've got a group of people who've got a walkie-talkie. They're all talking to each other on walkie-talkies. They're all on the same channel. Only one person can be talking at a given time. If 2 people talk on the same channel at the same time, same frequency, then they interfere with each other's voice. So you can only have one person talking at a time. You can have as many as you want listening, but only one person talking. So we could say, for example, that register 1 is talking. It's producing a number, putting the number onto the bus. The input isn't talking, but the output could be listening. The register 2 could be listening to what register 1 is publishing, but only one person can be talking at a time. And how do we enforce that? Well, the way that that is enforced is by gating the way that that things are connected to the bus via some sort of switchable buffer, and that buffer, which has to go between each thing on the bus and the bus itself, is switchable. So when the buffer is switched off, it's as if the register is completely disconnected from the bus. So when the bus is switched off, it's like you're not connected at all. If register 1's buffer is off, it's like register 1 isn't connected to the bus at all. For output, it's always connected to the bus for input, but these are output buffers. So whenever the buffer's turned off, you can't publish onto the bus. So at any given time, register 1 could be publishing, that could be switched on, and all the other ones could have their buffers switched off. So register 1 would be producing an output and putting it onto the bus, and register 2 could be listening to the bus and storing that value. So we could have, let's say, the number 170 in register 1. Register 1 could publish that onto the bus, so it would go out through the gate and onto the bus. The bus would be filled with the number 170. Anyone who wants to listen to it could listen and hear that 170. But we'd tell register 2 to read that data in and store 170 in register 2. And that is all that's happening in the register transfer machine. Okay, so having explained all that, I've got here my register transfer machine set up to do some register transferring. I've got the keyboard on the left here. So this keyboard is my 8-bit binary keyboard, and that shows a binary number. I've got a switch down here which publishes the binary number onto the bus. So if we put a 1, we get a binary 1 there. It goes on to the data bus of the register transfer machine, straight through and out the other side. And I've got my binary to decimal display plugged in on this end, so we see a 1. And I've got a lot of light shining on there. It's hard to read. I'm going to try and improve on that. Okay, so we have then, if I publish 1, we have a 1 on the screen. If I turn 2 switches on and publish again, we've got 3. So I'm publishing from the input device straight through the CPU and out to the output device, because the output device is always displaying what's on the bus. So that's just a way of seeing what's on the bus. Now I've implemented register 1, register 2 and register 4, and I've connected those up to these switches here. So we have publish for register 1, 2 and 4, and we have store for register 1, 2 and 4. So if I publish a 3 onto the data bus and store that in register 1, then the value of 3 is now stored in register 1. And if I stop publishing onto the bus, there's currently nothing on the bus. It's actually zeroed out because of the grounding resistors here. Yeah, so we've got the value of 3 stored in register 1. So let's take that off the keyboard, so that the only place that 3 could possibly be coming from is register 1. And if I publish register 1 onto the bus, there's the value of 3. So we've managed to transfer 3 from the keyboard into register 1. Let's pick another number. Let's get a nice on, off, on, off, on, off. That's if we publish that, here's the publisher for publishing the keyboard onto the bus. It's 170. So binary 10101010 is 170 in decimal. So if I publish that onto the bus and store it in register 2, we've now got the value of 170 in register 2. And if let's get rid of everything on the keyboard again. So the only place that 170 could possibly be now is in register 2. Publish register 1, there's that 3 that we stored in there before. Publish register 2, there's the 170 that we stored in there. Let's pick another number. Let's pick 15. So you go off, on is 15. Yeah, how can we see that? We publish it, publish 15, and store it into register 4. So we go, now we've got, that's not so easy to see that one, is it? Because they're green. Maybe I should switch that to being red. I'm going to do that. Well, I can't find a red LED anywhere, so I'm going to put a bit of paper there. How's that? Okay, so far I've managed to publish from the keyboard and shove numbers into the registers. But what I want to do, what a register transfer machine actually does, is transfer things between registers. So if we publish, let's turn everything off on the keyboard so we know nothing's coming from the keyboard. If we publish register 1, it's got a 3 in it. Register 2's got 170 in it because we stored that in there. And register 4 has got 15 in it. So if we now publish, let's say 3 and store in 1, we just moved the value from register 4 to register 1. Did I say publish 3 or publish 4? Anyway, we published 4 and we stored in 1. So if we now publish 2 and store in 4, we'll transfer the data from here to here. Now we haven't actually moved the data from there to there, we've copied the data from there to there. So the data is still in this register and we've just copied it to that one. So we could now publish, let's say, register 4 and store it in register 1. And now they've all got the same value in. So let's get an interesting different value. Let's do the first 4 bits high. So we publish the input, that's the number 240, and store it in register 4 maybe. Okay, so in order to do a publish and store, you've got to publish by holding that button down, and you've got to store by pressing one of these to move the data. So we've got to publish, let's say, let's publish 2, and let's store it in 4. So you've got to hold down the publish and momentarily press the store button to transfer the data. So there's 2 stages to it. There's a publish, and then while the publish is going on, there's a store. Now obviously inside a CPU there isn't some guy sitting there pressing publish and store buttons. There's a control unit that effectively presses the buttons for you. So what I need to build next is some sort of control unit to do these sort of things automatically. But also, there's more I can do on this register transfer machine, because you'll see there's a gap there and there's a few other bits and pieces missing here. Because so far I've got input devices. This is my keyboard putting data in. I've got an output device, which is reading the data off the bus, which is displaying my 0. And I have got registers which store and publish, but they don't do anything with the data. So there are other types of registers that you can have. One is a register that actually, does something with some data. So you could have an increment register. So you store a value in it, increase it, and put it back on the bus. Or I could have an ALU, which combines some data. So that's in fact what I've not quite implemented yet. So we'll be able to take this value and this value, combine them together, and make them appear in my third register, register 3, which I haven't done yet. So we might be able to add these 2 numbers together, or subtract them, or combine them in some other way. Also, I've got a slot here for a memory chip, because this register is a memory pointer register. It's pointing into that RAM. So I think I'll have a go with that one next.